after the inversion, most of the gate voltage drop across on the oxide. So this VOX is increasing compared to the threshold. Here you see, at threshold the VOX is just this part, and now with further increase the gate voltage VG, so the phi s does not change too much. So all the increase of the gate voltage actually is reflected as the increase of the gate oxide voltage. So this one increase, and this one almost no change. Any questions here?
Can you explain why the electric field only exists in the oxide band? Or is that the case?
So the electric field will get larger and larger in the oxide. And then in the semiconductor, in the silicon, there's still some electric field. And this is because the electric field, in the voltage potential is the slope. You can see the slope. So here, this phi s does not change too much after the inversion. So then this slope doesn't change too much, so the electric field is kind of small. But this part, this VOX, is going to increase as you increase the gate voltage. So this one becomes steep. So the slope is the electric field. So that's why you see larger and larger electric field across the oxide. So this is the relationship between those three variables. And next, we are going to repeat this process by looking at the band diagram. So here, again, the same condition, the doping density, Na, 10 to the power 18. And then this is initial flat band condition, where the gate voltage equals to 0. But the Fermi level of the metal lined up with the Fermi level of the p-type silicon in this case. So here everything is to the scale using this kind of condition. So let's apply the gate voltage. And then, as you can imagine, when you apply positive voltage to the metal side, we are going to push down to the metal Fermi level. Let's do it. So this is the initial condition. And now you apply small voltage. This is like 0.2 volts. Then you see the solid line is the band diagram at this condition. This is the dash is the initial condition. Dash line is the initial condition. So let's do this. You see now we keep increasing. So you see the Fermi level of the metal is pushed down by the gate voltage, and then the band is bent down. So this is, but the Fermi level, this red line, is flat, okay, in this process. So that means initially you see at the surface, the Fermi level, the red line, is close to the EV. But as that means this is p-type, right? But as you push down the band, so this Fermi level at the surface is going to be close to the EC conduction band. That means it becomes n-type. And we define here when the phi s equals to 2 phi b, this is the threshold condition. So this phi s is actually bent down for this band. This is the phi s. Or in other words, if you look at the distance of the Fermi level to the conduction band edge, EC is the same distance where here at the very substrate, the Fermi level distance between the EV and here the EC. So you see here the inversion. In the substrate, the Fermi level is, let's say, above the EV by delta E. Now this, at the surface, the Fermi level is below the EC by the same amount, delta E. So this is the threshold condition. Any questions? And then above the threshold, we keep applying the gate voltage. Then what will happen here is you see this surface potential will not change too much because it's already very close to the conduction band edge EC. So, but you keep applying gate voltage. So the only thing that will be bent is this part, the oxide band. You see that if you further do this, then the oxide band will become more bent. This agrees with the diagram earlier. We said that above the threshold voltage, then most of the voltage drop of the gate voltage is on the oxide, VOX. So, any questions? So, I think your last homework is related to this kind of band diagram.